Okay, and the next contribution will be presented by myself. So that's a modified Weibull Stress approach, a modified Beremin model to predict specimen geometry effects in pressure vessel stills. And my next Claudio Ruggeri, I'd like to acknowledge my co-author, Professor Bob Dodds, which was supposed to come here and had to cancel his flight because of Air France strike. So that's the outline of my presentation. Because of time restriction, I'll be I will skip many details. I am sure that everybody's anxious to get ready for the conference dinner. Essentially, I will present talk about the constraint laws in pre-cracked Charpy specimens versus large specimens, and the toughness correction using the modified Beremin model, and application to predict the T0 for a standard pressure vessel QA 515 pressure vessel. So very simply, so the motivation is to assess the material degradation in reactor pressure vessels. Usually the degradation is caused by fast neutrons caused by the fissile reaction. The fissile reaction, the fast neutrons will cause a large number of defects, which will eventually cause a reduction in fracture toughness. So probably the most widely used procedure to evaluate the material degradation is the master curve. Many people have talked about the master curve. I won't go into detail. Essentially, is the T0 at the KJC of 100 for a standard 1T specimen, so 1 inch specimen. Some of the key features are shown here. I'll focus here on the thickness effect correction of JC value, or JC values, or KJC, whatever as you want, using a simple weak link model. When we're using the pre-cracked Charpy specimens, okay. So the issue then is the difference between a smaller specimen and even smaller. We haven't seen here specimens with 0.4 pre-cracked Charpy, 2 millimeters, 3 millimeters thick. But the reason to use these is because it facilitates the fracture testing. And it's very attractive because of material availability. Okay? However, there is a potential serious issue here because of the breakdown in the mechanical similitude between a small specimen and a nuclear reactor pressure vessel. And this is because of the strong loss of constraint and strong development of plasticity. From these results shown from Dr. Nestad at the Oak Ridge National Laboratory, you can see here a difference in when evaluating the T0 between T0 determined from pre-cracked Charpy, it's a red one, and from the 1T CT specimen. So the difference can be very large, a shift of almost 20 degrees. And that's the trend that we have here. So as we decrease the specimen thickness, in general, the T0 also decreases. Okay. So how to incorporate these and get a more accurate T0 evaluation? I won't go into detail, but this is the basis of the Beremin model. Is a random distribution of microcracks. Fracture is controlled by the critical microcrack and the inside the fracture process zone. And after some manipulation of the microcrack distribution, and you arrive finally at the Beremin Weibull Stress. With this, there are many definitions. Well, simply is the integral of the principal stress raised to the Weibull modulus. Okay. One of the drawbacks of the Beremin model is the Beremin Weibull Stress relies on the assumption that the rift-like microcracks, the carbides, the microcracks are nucleated from the carbides, they inform when yielding takes place. So the statistical distribution of microcracks remains unchanged with increasing load and deformation. So we want to, in a very simple way, incorporate the effects of blast strain while at the same time keeping the general character of the Weibull stress. And that's what we did. we took the again the microcrack distribution, and then we assumed that only a fraction of those microcracks are eligible to propagate. In other words, in the fundamental Beremin equation, we introduce here a C sub C, which represents the fraction of the microcracks, which will eventually propagate. And then the Beremin Weibull stress becomes the same stress integral where CC comes inside. And then we can think of many possibilities for the function C sub C. I'm showing here only two possible functions. One is a ad hoc assumption, which is an exponential dependence of class strain. And the other one is the particle fractal distribution proposed by Kim Walling. Well, correct me if I'm wrong, but about 5 or 6 years ago, which is a revisiting of the original Walling and Toroni model about the statistical distribution of microcracks. So the classic strain will enter here through the particle fractal stress, because you can see here this is a Weibull distribution for Weibull modulus of alpha, and sigma sub PRS is a let's say a particle reference stress. Okay, and also we have examined this work, the modified Beremin. So in the original Beremin work, there is a modification of the Beremin stress where there is another exponential term here. Okay. Okay. Then we are going to predict the T0 from the pre-correct Charpy data using these modified Beremin work. This is the standard. This is the standard 515 steel. It's a high hardness steel. This is the transition curve. Usually we have about 300 megapascal room temperature and 320 at -20. The tests, we test the large SCV specimen, 1.2T with 30 millimeter. This is the pre-cracked Charpy. The scatter is described by conventional Weibull distribution. For the Weibull stress prediction, actually it doesn't matter too much whether you use a 3-parameter or the 2-parameter. We are sticking with the 3-parameter because of the connection with the master curve. Okay, and these are the toughness distribution here. This is the deep crack SCV, and those are the shallow crack -10, and also the pre-cracked Charpy -20. We didn't see any ductile tearing, which is good because then you can apply directly in a straightforward manner the approach. So this is for the deep crack and shallow crack, and also for the pre-cracked Charpy. No ductile tearing, even though we did see here much larger plastic deformation. Just to give you an idea, so almost pure cleavage in all the specimens, and this. And this is the T0 estimate using the large specimen, which provides us with a benchmark. So this is using the standard procedure, ASTM 1921. So the T0 is minus 41 degrees. And then we run the procedure. The Weibull stress relies strongly on finite element analysis. So we use work 3D, incorporating large strain, large nuclear change analysis. These are the models for the SCV specimen and pre-cracked specimen. And essentially the calibration, it's probably one of the key parts of this procedure. You have to run a finite element analysis, you have to do the testing, you have the toughness data, and then you have to calibrate all these parameters using the toughness scaling model. First, to calibrate then the Weibull modulus, which is assumed to be independent of temperature within this small range. We are testing between -5, -10, -20, -30 when we did the analysis. So first, after we calibrate the Weibull modulus, we then can calibrate the classic strain function by assuming that the Weibull modulus remains unchanged with the different parameters for the classic strain function. This is reasonable because when the classic strain effect there is no classic strain effects. So the model should bring the same prediction as the Beremin model. That's the basic idea. So that's the calibration of the Weibull modulus using the toughness scaling. Essentially, it's using a correlation between the deep and shallow crack here. So we're predicting J0 for the deep crack from J0 from the shallow crack. And then we can see here that the Weibull modulus about 11. And then we calibrate the function psi sub c. Again, so we fix M0, and then we vary the particle reference stress, it's the characters reference stress, by varying, and again, choosing the value which brings the best prediction between the shallow crack and the deep crack. And the same for the exponential dependence model. Again, we can calibrate the lambda, again for a fixed value of the lambda. And this is what we have here. So the prediction using the two models is for the particle distribution, for a fixed value of M0 and the calibrated parameter. So it's 6,500 megapascal here, from this 0.3. You can see here the difference. And this is the distribution of the JC. Okay, then we afterwards we convert this to KJC and then calculate the T0. I can see here the very good prediction of the SCB, deep crack SCB distribution. Only the lower tail here a little bit offside, but generally it predicts very well. The exponential dependence is a little conservative, so it shifts the prediction to the left. And this is the Beremin model, which is very conservative because it doesn't include plastic strain effects. So again, just to remember, the T0 is minus 41 degrees, and those are the T0 predictions using the standard Beremin, the modified Beremin, which has a exponential term, which is a function of the black strain, exponential dependence model, and the particle distribution from the water, and then fixed Weibull parameters. So this is the predicted characters toughness here, and these are the predicted T0. You can see here that the Beremin is conservative. The T0 is minus 20. The modified Beremin overshoots the prediction actually. We don't have time here, but I can discuss later why there is this overshooting. The exponential dependence is less conservative, and the T0 prediction using the particle distribution model is within 1 degree of prediction. So it provides a very good agreement. So finally, okay, sorry, I run my time. The simplified particle distribution is, within this work, is the best plastic strain correction. Of course, there is a rather strong sensitivity of fractal predictions of the Weibull parameters, and this is still a major concern. So what we're doing here is a further validation of the approach. A calibration procedure which is simple and still less sensitive to analysis details. So calibration is still a very key issue here. And also the use of other forms to define the fraction of Microcracks or the C sub C function. Okay, thank you very much. I did my best to